I'm going to be going over solutions to every hard geometry problem on the SAT. This is part 3, specifically all of the geometry questions listed as hard that are about right triangles and trigonometry. All of the problems will have 3 on their difficulty, 3 out of 3. All of them have the same scale, right triangles and trig, in the geometry section. Before you start, you can check the video description. All of the question IDs will be listed along with the timestamps with the exact minute and second that the question explanations start, and a brief description of each question. In triangle XYZ, angle Z is a right angle and the length of YZ is 24 units. If tangent of X equals 12 over 35, what is the perimeter in units of triangle XYZ? All right, so Z is our right angle. We can draw a right triangle here, put Z down here. Means X and Y will be the other ones. And it says YZ is 24. If tangent of X, tangent means opposite over adjacent, right? We can think of like tangent of theta, it'd be TOA if you did SOHCAHTOA. But opposite means across, so 24 is the one that's opposite, and adjacent is the one that's touching that's not the hypotenuse. Hypotenuse over here. So this is our adjacent. This XZ actually should be longer. I didn't draw this correctly, but it doesn't matter. It's not supposed to be to scale. So tangent of X is going to be equal to ZY, which we already have here, or YZ is 24, over XZ. We don't know what XZ is yet, but we know that that's equal to 12 over 35. So you can just quickly look at it. 24 is double 12, so you could just double 35 and know that it's 70. So this should be 70 over here. If you feel more comfortable doing the cross multiplication, you do XZ times 12 and 24 times 35. Then 24 times 35 divided by 12 would end up being equal to, like the 24 divided by 12 will make 2. So you get 2 times 35, which is 70. If you want to find the third side, you could use the Pythagorean Theorem. 24, one of the legs squared, plus 70, the other leg squared, is going to be equal to the hypotenuse squared, so xy squared. You just do it that way. Other thing you could do, if you know your Pythagorean triples, 12, 35, 37 is actually one of the Pythagorean triples, which means it's a set of 3 relatively prime integers that would work for a squared plus b squared equals c squared. And in this case, this is just a 12, 35, 37 scaled up by a factor of 2. You're doubling the 12, which makes 24. You're doubling the 35, which makes 70. And that would mean that we should double the hypotenuse, 37, to make this into 74. All right, so before we start, the answer for this part will be 74, and then you just add those 3 up. It would be 24 plus 70 plus 74, which gives us 94 plus 74, and that will be equal to 168. All right, so 168 will be our perimeter. We could even just go based on the fact that it's 24 and 70. We already know those. If you add those, they're already bigger than 71 and 84, so we know it's between A and B. Now, if you didn't know your Pythagorean triples and want to see how you could do it, again, you just plug in your Pythagorean theorem. So 24 squared would give us 576, plus 70 squared would be 4,900. That's going to be equal to xy squared. 576 plus 4,900 would give us 5,476. And you would just take the square root of both sides to get xy alone. Square root of 5,476 gives us 74. Right, which was the same value that we did down here using the Pythagorean triple scaled up by a factor of 2. We have xy is 74. Again, the same thing. We would use those 2 values we already had, 24 plus 70 plus 74. The perimeter of a triangle is just adding up all the sides. And it's the same thing we did down here. You get 94 plus 74, which is equal to 168. Again, if you know your Pythagorean triples off the top of your head, then that makes it, will save you, maybe like 10 or 15 seconds of doing this, and just you'll feel a little more confident in it. But you get a calculator, so you can easily do the Pythagorean theorem for even big numbers. In triangle XYZ, angle Y is a right triangle. So I think we're going to have a lot of right triangles in this set, based on the topic is right triangles and trig. But we've got Y, and then this will be X and Z. So note that this one, Z, was the right angle. This one, Y, is the right angle. Don't assume it's going to be the same triangle. The measure of angle Z is 33 degrees. Okay, this is actually drawn not perfectly to scale, obviously, but the Z is the more acute angle of the two, Z and X. And length YZ is 26 units. So this is 26 down here. If the area in square units of triangle XYZ can be represented by the expression K tangent of 33 degrees, where K is a constant, what is the value of K? All right, well, first, tangent of 33 degrees, that's tangent of Z, is going to be equal to the side opposite the Z, so that's X over Y, divided by the side adjacent, which we know is this yz, which is 26. So we've got tangent of 33 equals xy over 26. Now, for the area of this triangle, because it's a right triangle, the two legs can serve as the base and the height because they meet each other at a right angle. So each of them is the altitude to the other one. So in that case, we could do the area is equal to 1/2 times 26, which is the side down here, times this side that would serve as the height if 26 is the base, so that's xy. 1/2 times 26 times xy is 13xy. All right, so we want something that's equivalent to 13xy that uses this tangent of 33 that we have over here. So you'd have to think, what would you need to multiply xy over 26 by to make it equal to 13xy? So we can rewrite that down here. Xy over 26 times k, and k is the thing we're trying to solve for here, because this is, right here, this is tangent of 33. So k times xy divided by 26 is equal to the area, which our area we said is 13 times xy, which we use that 1/2 times base times height formula to get that. All right, now we can divide both sides by xy. So we can get rid of the xy's because you have one on both sides. That cancels out over here, cancels out over here. That leaves us with k times 1 over 26, or in other words, k divided by 26 is equal to 13. Now to get k alone, we're just going to multiply both sides by 26. 26 is cancel over here, and that leaves us with k is equal to, well, that would be 13 squared times 2. So 169 times 2, 338. All right, and there's no multiple choice, so we'll just say that's our answer. And just to check it, let's type in tangent of 33 degrees on your calculator. Make sure you're in degree mode. It gives me, the calculator estimates tangent of 33 degrees to be about equal to 0.649407. And now if we multiply that by 338, it gives me 219.49976, da da da. All right, it's an irrational number, goes on forever. Now, if we wanted to find what xy was, we would say it's 26 times tangent of 33, right? Just by using this thing here, we'd multiply both sides by 26. So if we used the area formula, it would be 1/2 times 26 times what we just said, xy equals 26 times the tangent of 33. So we would do 0.5 times 26 times 26 tangent of 33. And that is also about equal to 219.4997665, dot, dot, dot. All right, so they give us the same value. So 338 is correct there. Triangle ABC above is a right triangle, and sine of B equals 5 over 13. That's opposite over hypotenuse. The ratio of AC to AB is 5 to 13, and they give us that AB is 26. So we don't know what AC is yet. AC over 26, this is AB, the hypotenuse. And again, that's because sine of theta is equal to opposite over hypotenuse. Right? So in SOHCAHTOA. So AC over 26 is equal to this ratio they gave us, 5 over 13. All right, we can use that to find AC by just multiplying both sides by 26. And I mean, you could also see this is just 13 doubled, so AC should be 5 doubled, so it should be 10. But if we just multiply it like this, that cancels. 26 divided by 13 is 2. 5 times 2 is 10. All right, so we know AC is 10. We're actually solving for BC, not AC. But you could recognize that this is another Pythagorean triple just scaled up. So one of the Pythagorean triples is 5, 12, 13. This is probably the most popular one after 3, 4, 5. And they just scaled it up by a factor of 2. So they doubled the 5 to make 10, doubled the hypotenuse to make 26. And that would mean they double this other leg, 12, to make 24. All right, so this should be 24 up here. Now, if you don't remember 5, 12, 13, or you don't feel confident in it, you could also do the Pythagorean theorem. Right, so a squared plus b squared equals c squared. We have a, we just solved for that here using the sine function that they gave us. So that'd be 10 squared plus b squared is what we're solving for, or we're solving for b, but we'll get b squared alone first, and that will be equal to 26 squared. And that's the hypotenuse, the c that they gave us. So this would be 100 plus b squared is equal to 676, 26 squared. And then you would just subtract 100 from both sides. Get b squared is equal to 576. And then take the square root of both sides to get b alone, which would be 24. Right? So in either case, you'll get b is 24, b being the side BC. All right, right triangle ABC is shown. What is the value of tangent of A? We know it's a right triangle, so this is a right angle, this is 30. All of the angles have to add up to 180, so it's going to be a 30, 60, 90 triangle. 30 plus 60 makes 90, 90 plus 90 makes 180. What is the value of tangent of A? Tangent is opposite over adjacent, so we need to find the length of this side and this side. If you know your 30, 60, 90 ratios, which I think will be given to you on the day of the test in your reference sheet, then you know it's going to be the side opposite the 30 would be x, the side opposite the 60 would be x times the square root of 3, and the hypotenuse would be 2 times x. So they give us that 2x equals 54, which means that x is half of 54. So x over here, the side opposite the 30, would be 27. And then the side opposite the 60, the x root 3, would be 27 times the square root of 3. Right? We write that out, 2x equals 54, divided by 2 means x equals 27, x root 3 equals 27 root 3. So just using that, if you wanted to do the tangent of 60, it'd be 27 root 3 over 27. So opposite over adjacent would be 27 root 3 over 27, and the 27s will cancel out, leaving you with the square root of 3. It's one way you can do it. Again, you should know your special right triangles, but they will be given to you. But if you don't feel comfortable with the special right triangles, or you feel like you messed them up, as long as you can find that A is 60 degrees, so up here, then you can just type into your calculator the tangent of 60 degrees, and it gives you that the tangent of 60 is equal to, and make sure you're in degree mode, 1.7320, blah, blah, blah. And then you just have to figure out which of these is equivalent to that, right? It's going to be an irrational number, but you can see which one's close. So we could type in the square root of 3 divided by 54, 0.03207, right? That's way too small, it's not that one. We've got 1 divided by the square root of 3, so they didn't even rationalize the denominator for you. It should be root 3 over 3, but whatever. They give us 0.57735, also too small, right? We want it to be 1.73. Then the square root of 3, so this is what we got for our answers, it should be right, is 1.73205, right? The same thing over here. And then 27 times the square root of 3, this will be way too big. That's 46.76537, dot, dot, dot. All right, so it's not that one. All right, so that's another way you could do it, as long as you can find that 60 degrees, which would be a question I could even put on the easy one. Just do the tangent of tangent of 60 degrees, and then evaluate it and compare the tangent of 60 degrees to all of those radicals when written out as decimals. So that's kind of like a little cheat code you could do if it's a multiple choice one. I would recommend making sure that you're comfortable enough with special right triangles that you could figure it out like this. In the triangle below, what is the value of sine of x? Sine of x is going to be opposite over hypotenuse. Well, sine of anything is opposite over hypotenuse. Right? If it was SOHCAHTOA, sine is opposite over hypotenuse. And in this case, x is here, so opposite is the 16, the hypotenuse is 23. So is that all there is to it? 16 over 23. I'm not sure why this one's in the hard section. That's odd. Okay. Maybe because the other ones, they would say like what's sine of A, and it would actually be talking about the side, but x degrees. Yeah, it doesn't matter like how much you scale up the triangle. If it's x degrees there, it would be the same thing. All right, so 16 over 23. A graphic designer is creating a logo for a company. The logo is shown in the figure above. The logo is in the shape of a trapezoid and consists of 3 congruent equilateral triangles. You can see it kind of overlaps with the question ID up here, but it goes like that. That's the trapezoid they're talking about, and you've got 3 of these triangles. 3 congruent equilateral triangles. If the perimeter of the logo is 20 centimeters, what is the combined area of the shaded regions in square centimeters of the logo? So we want just the shaded area. So we want this triangle and this triangle. Now we could start, they give us the perimeter is 20, and we can see how many of the sides of the equilateral triangles that encompass. So we've got one there, one there, one there, one there, one there, right? So going around, there are 5 sides of the triangle that make up the perimeter of this trapezoid. So we can say 5x is equal to 20, which means x is equal to 20 divided by 5, which is 4. So the side length of one of the triangles would be 4. Now to find the area of an equilateral triangle, you can divide it into a 30, 60, 90, or two 30, 60, 90 triangles. So basically, right, equilateral, we know all of the angles are the same, all of the sides are the same. So all of the angles are 60 degrees, 60, 60. They have to all add up to 180. So if we drop down an altitude that's also an angle bisector, it would make it 30, 60, 90 over here and 30, 60, 90 over here. Now that's going to cut that side length of 4 in half. Right? So if this whole thing is 4, then when you drop the altitude down, this half will be 2, this half will also be 2. This side up here will still be 4. Now using that same side ratio of the 30, 60, 90 right triangle we just did in the previous problem, 30, 60, 90, we know the side opposite the 30, if that was x, then the side opposite the 60 would be x times the square root of 3, or x root 3, and the side opposite the right angle, the hypotenuse, would be double the smallest side, so 2 times x. All right, so we could see that. This is actually part of how you can derive that, is you've got, right, the small side 2 is half of an equilateral triangle, and the hypotenuse would be one of the sides, so double it. So 2, 4, and that means that the height will be 2 times the square root of 3. Now, if you don't remember the special right triangles, or again, I think it's given, but if you don't feel comfortable using it, you could also just do the Pythagorean theorem. It will also give you, using this 4 and this 2, that this height is 2 root 3. The height is 2 root 3, and the base is still 4, right? It's the entire base. Then you can find the area of one of those triangles as 1/2 times the base, 4, times the height, 2 root 3. So this is of one triangle. That gives you half of 4 is 2, so 2 times 2 root 3 equals 4 root 3. So that's for one triangle, right? One of these. The shaded area is 2 of them, so we have to double it. Area, let's call this area shaded, equals 2 times the area of a triangle. So 2 times 4 root 3 is going to be 8 times the square root of 3, right? It's just double the area of one of them. So that's how you would do that. Again, knowing your 30, 60, 90 right triangles will be really helpful with these. There's actually a formula if you memorize it. It's not necessarily worth memorizing because you can find the height there and just use 1/2 base height. But the area of an equilateral, if you have one of the sides, is going to be equal to the side squared times the square root of 3 divided by 4. Now the reason for that is basically you're multiplying 1/2 times the base, which is the side, times the height, which we know is going to be half of the side times the square root of 3. So we could call that s root 3 over 2. And that gives us s times s is s squared. The square root of 3 will just stay up there in the numerator. And then we have 1/2 times another 2 in the denominator. So that's 2 times 2 is 4 down here. All right, so s squared root 3 over 4 is the area of an equilateral triangle given the side. You know, that really, it could potentially help, but it's not something you need to know. In this case, we would know the side of the equilateral was 4, so it would be 4 squared root 3 over 4, which would give us, right, 16 root 3 over 4 equals 4 root 3, or you could even have canceled one of these 4s. So that's the area of one of them, and then again, you had to double it to get to this 8 root 3, which is our final answer. The perimeter of an equilateral triangle is 624 centimeters. So we know all 3 sides are the same. They're going to add up to 624. You can say that 3 times the side length equals 624. Right, so before I solve that, let's read the rest of the question. The height of this triangle is k times the square root of 3. All right, so this is k root 3 right here, where k is a constant. What is the value of k? Well, as we just talked about in the very previous problem, the height of an equilateral triangle is going to be something you can solve using a 30, 60, 90, and it's just going to be the square root of 3 times half of the base. But whatever, we could redo that in case anyone skipped to this problem. But first, let's find the side length. That's going to be 1/3 of 624. Right here we have 3x equals 624, so just divide both sides by 3. Gives us 208. All right, so we've got basically this triangle has 3 sides of 208, and we're trying to find the height. As we said in the previous problem, when you drop down this altitude, it's also an angle bisector, and it's a median, so it's going to cut this other side in half. So it's going to make this into, this angle was already 60, right? All the angles in a right triangle or an equilateral triangle are 60. So 60, it cuts that 60 into 30 over here and 30 over here. And it's going to cut this 208 into 2 halves of that, which are 104 over here, 104 over here. Now for a 30, 60, 90, the ratio of sides, the smallest side is the one opposite the 30. That's, you could call that x. The side opposite the 60 will be x times the square root of 3. So it's square root of 3 times bigger than the smallest side. and then the hypotenuse should be double the smallest side, so that's 2x. In this case, we could see, right, the side opposite the 30 is 104, the hypotenuse is double that, 208. So our height here should be the small side, 104 times the square root of 3. So our height equals 104 root 3, and they also said that's equal to k times the square root of 3. So we need to solve for what k is, just divide both sides by the square root of 3, and you'll be left with k is equal to 104. In triangle ABC, angle B is a right angle. All right, so let's draw a right triangle. Angle B is a right angle. AB is 10 root 37, so 10 root 37, and BC is 24 root 37. What is the length of AC? So what's interesting here, this is another 5, 12, 13 right triangle. I told my students in class that 5, 12, 13, and 3, 4, 5 are the most common to show up on the SAT. And I think that was true when I took it, and I believe it's still the case. Just a lot of times the 3, 4, 5 and the 5, 12, 13, they're going to scale them up. I was telling them usually they scale it up by a factor of 2 or 3. In this case, they're scaling it up by a factor of 2 root 37. So how I recognize this was, right, it has the 10 and the 24. So a lot of times you'll see one that's scaled up by 2. So 5 becomes 10, 12 becomes 24, 13 becomes 26. But in this case, they did that, and then they multiply both sides by the square root of 37. So again, our scale factor from 5, 12, 13 to this is going to be 2 times the square root of 37. That's what you have to multiply each side by to make it match up to this, right? So that would mean we have to do the same thing for 13. 13 times 2 root 37. Well, double 13 is 26. 26 root 37. Right, so that's option B. That would definitely be how I would do this problem, is try to look for, it's a lot of times when they do right triangles, they give you weird values. It's going to be a Pythagorean triple. So like a common right triangle with integer side lengths just scaled up by a certain amount. This is the first time I've seen one that was scaled up like this, but that's probably something they've added to the new form of the SAT. Now, if you don't feel comfortable with your Pythagorean triples, if you don't know 5, 12, 13, for instance, what you could do is just do the Pythagorean theorem. And it even works if you have these weird numbers. So 10 root 37, just make sure that you're squaring that entire thing. So 10 root 37 plus, parentheses, 24 root 37 squared is equal to the hypotenuse squared. What we're trying to solve for is the hypotenuse. You could do this in your calculator, but 10 squared is 100. The square root of 37 squared, square root and squared basically will cancel out there. Or you could think the square root of 37 is what number times itself is 37. Well, you're timesing it by itself now. So 100 times 37. Plus 24 squared is going to be 576. And then you multiply that by the square root of 37 squared is again 37. And that should be equal to c squared. If I type in 100 times 37 plus 576 times 37, it gives me 25,012. So that's equal to c squared. Now if I want to solve for just c, which will be our answer, the length of AC, we do the square root of both sides, leaving us with c is equal to the square root of 25,012, which is 158.1518258 . It's an irrational number, keeps going forever. Now, there are some calculators where you could just push a button and get it to be in simplest radical form. If you have one of those, then obviously that would return you the right answer. Right? So you'd get it as 26 root 37, and it would be much easier. If you don't have a calculator that can do that, or if you don't know how to do that on your calculator, another option is just to type all of these into your calculator and see which one is equal to 158.1518. It'll be another irrational, well, all of them will be irrational numbers, but you can see which one is the same irrational number. All right, so we can write 14 times the square root of 37. That gives us 85.158, that's too small. Then 26 root 37, right, based on us having done it before, this should be the right one. It gives us 158.1518258. That's the same one. All right, so it still gives us B. And just to confirm, the other ones are all different. 34 root 37 be 206.8139 ... It's not that one, too big. And then the square root of 34 times 37, both of them in the square root, that would give us 35.46829. That's too small. Right, so B would be the answer either way. I recommend knowing your Pythagorean triples, at least 3, 4, 5, 5, 12, 13, and try to get yourself accustomed to recognizing when they're being scaled up. But, again, when you don't know it, you just use the Pythagorean theorem. It does burn a decent bit more time because you could do this part almost instantaneously. Like I know I had to explain what I was doing, but if I had this problem, I would actually probably be able to see, 10, 24, this is a 5, 12, 13. So double 13, 26, 26 root 37. Like you could do it in basically 15 seconds if you are really comfortable with Pythagorean triples and scale factors. But it didn't take too much time to do the Pythagorean theorem. Just make sure that you're comfortable typing it into your calculator and doing it quickly. Now we've got a right triangle inside of another right triangle, and they're going to be similar because they share this angle B. So that means that angle E is the same as angle C. Also, does it say they're parallel? I mean, if they both are perpendicular to the same line, then they are parallel to each other. And that means that we've got corresponding angles of a transversal through two parallel lines, right? So these two angles are the same, angle B is shared. Now, that means that the ratios of the sides will also be the same because they're similar triangles. So tangent of B equals 3 over 4. We know that tangent is opposite over adjacent. So that means the ratio of the opposite side to the adjacent side, so DE over BD will be 3 over 4. And similarly, for the big triangle, opposite is AC, adjacent is AB. So that would also be a 3 to 4 ratio. If BC equals 15 and DA is 4, so this entire side here is 15, and DA is down here is 4, what is the length of DE? All right, well, the other thing that we can realize, if it's 3 and 4, that means it's basically a scaled up 3, 4, 5 right triangle. That's another Pythagorean triple. So if the long side is 15, that means it's 5 times 3, so you scale that up by a factor of 3. So this side, which is the side that corresponds to the 4 on the 3 over 4 of the tangent, should be 4 times 3. Right? It's the 3, 4, 5 scaled up by 3. So that side would be 12, and then this side should be 9. All right, so that's something that we already know, and then you could use that to figure out what BD is, because if DA is 4, you just take 4 away from 12, that leaves you with 8 up here, and 8 is 4 doubled. So this one, BDE, this triangle, the smaller triangle up at the top, is a 3, 4, 5 scaled up by a factor of 2. So that means 5 is doubled, so that'll be 10 up here. 3 is doubled, that'll be 6. All right, so we've got 6, 8, 10, and then down here it's 9, 12, 15. Now they say, what's the length of DE? DE, we just said, is 6. So if you know your 3, 4, 5 triangles, that makes that one that easy. Yeah, that's definitely the easiest way to do it. Now you could also do something with inverse tangent to find the angle, and then use the angle to use the hypotenuse to find some of the other sides. So then you could find the length of AB. Again, you would still end up getting 12, and then you could use that 12 and the 4 to figure out that this side up here is 8. And then you could use, once you have that BD is 8, you would do 8 times the tangent of B, so 8 times 3/4, because that would be opposite over adjacent times 8, the adjacent. So the adjacents cancel out, leaving you with just the opposite, which would be 6. So you could do it that way, but I really recommend make sure you're comfortable doing the 3, 4, 5 right triangles scaled up, because as I said, that one shows up the most. 5, 12, 13 is probably the second most, and generally they're going to be scaled up. An isosceles right triangle has a hypotenuse of length 58 inches. So isosceles means that both of the sides are the same. It also means that the angles that are not the right angles are going to be 45. So you got 45, 45, 90, and okay, they said the hypotenuse is 58. Also, for a 45, 45, 90, so an isosceles right triangle, the ratio of the sides will be x, x, x root 2. Obviously, the largest side is always the hypotenuse for right triangles, so that's the side that's multiplied by the square root of 2. So if you want to find x, you could say x times the square root of 2 is equal to the hypotenuse, 58. Then to get the x alone, you would just divide by the square root of 2 on both sides. So x is equal to 58 over root 2. Now, if you want to put that in simplest radical form, you want to get the radical out of the denominator, so you can call that rationalizing the denominator. And you can multiply by a form of 1. So anything divided by itself is 1. We could do the square root of 2 divided by the square root of 2. So if you multiply by this, it doesn't change the value, right? It's the same as if you multiply something by 1, it's still itself. But what this does is in the denominator, root 2 times root 2 is just 2, right? It's root 2 squared. So we're left with 58 root 2 over 2. Now you can see there's still a radical, but the radical's in the numerator now in the top instead of in the bottom. And then just half 58. So 58 divided by 2 is going to give us 29, and then we still have the square root of 2. All right, so these sides are 29 root 2 and 29 root 2. Now some people will just leave it as 58 over root 2. If you want to do that, you just have to type all of these options in and see which one has the matching decimal. But as long as you are comfortable rationalizing the denominator, if we want to find the perimeter, we just add up those three sides. So 29 root 2 plus 29 root 2 plus the 58 we were given. Now you can't combine these two as 58 because it doesn't have a square root of 2. But basically think of if a square root of 2 is a thing. So like maybe a pencil is a square root of 2. We've got 29 of these, and then we've got 29 more of them. So that's a total of 29 plus 29 is 58 square root of 2's. And then you also have this 58, just, integers over here. So we leave those two separate, 58 root 2 plus 58. You can see that's equivalent to C. They just did the commutative property of addition. You can switch the order. If you're adding two things, it doesn't matter. Now, if you don't feel comfortable with rationalizing denominators and finding it that way, and you just wanted to leave it as 58 divided by the square root of 2, so you'd say 58 over root 2, 58 over root 2, then you would end up with this, right? So 58 over root 2 basically times 2 plus 58, because you have two of them. So if you type this into your calculator, 2 times 58 divided by the square root of 2 plus 58, it gives you 140.024386, and an irrational number, so it keeps going. Now, that's not going to show up in one of these options here because they wrote them in simplest radical form. And even if you have one of the calculators that writes in simplest radical form, it might not be able to return it as the sum of integer and radical. Some of them are more advanced. But what you could do, as I've said in previous ones, if you have a decimal answer and you want to see which of the multiple choice options it matches to, then you can just type all of those multiple choice options in and see which one is the same. So you can see which one will give you this 140.024, whatever. So 29 times the square root of 2 gives us 41.012, that's too small. 58 times the square root of 2 gives us 82.024, ... That's also too small. And then if we have 58 plus 58 root 2, that gives us 140.0243866. Okay, that matches, that's good. And just to show it's going to be different, this one is obviously going to be bigger because you're just doubling the second part. But 58 plus 116 times the square root of 2, this would be 222.048, right, that's too big. So C would be our answer. And again, I would recommend being comfortable enough with radicals that you can rationalize and just find the answer without using a calculator and without using the decimal answers. But this is another option in case you don't feel comfortable with that, or even if you did it and just you want to check that you did it correctly. A rectangle is inscribed in a circle such that each vertex of the rectangle lies on the circumference of the circle. The diagonal of the rectangle is twice the length of the shortest side of the rectangle. All right, so let's see what we've got so far. We have a circle, and there's a rectangle inside of it. And the diagonal of the rectangle is twice the length of the shortest side of the rectangle. So if this is x, then the diagonal is 2x. The area of the rectangle is 1,089 times the square root of 3 units. What is the length in units of the diameter of the circle? Okay, well, the diameter of the circle is this diagonal of the rectangle. That's just always going to be the case for a rectangle inscribed in a circle. It's the longest way to go from there to there. If it's inscribed, it's fit as much as it can fit. Right? So there's nowhere you can move it where there'll be a longer diagonal. Now, because this is an x and a 2x, I'm recognizing, and rectangles have all right angles, so I'm recognizing that this is a 30, 60, 90 right triangle, just by the ratio of the sides. Right, now this one's the 30 because it's the one across from the x, and the hypotenuse should be double the side opposite the 30. So x, 2x, that would mean that this side down here is x root 3. We don't actually need that for this case. Well, actually we do, because they gave us the area. So if you can do that, then we know the area of a rectangle is length times width. So in this case, the length is x root 3. Right? We just used that 30, 60, 90 ratio to find that. And the length of the shortest side is x, right? We don't know what x is yet, but we do know the area is 1089 root 3. So 1089 root 3 is equal to x times x is x squared times the square root of 3. Now to get x squared alone, we can divide both sides by the square root of 3. That cancels out the root 3 over here and root over here, and that will leave us x squared is equal to 1089. And now to find x, you just do the square root of both sides. We don't have to worry about negative solutions because it's a geometry problem, right? You can have a negative length. So the square root of 1089 is 33. So that means this shorter side is 33. And that's not our answer yet. We have to now use this to find the hypotenuse. The hypotenuse is double the shortest side. So 2x is just going to be double 33, which is 66. So it's another one where 30, 60, 90 right triangles will really come in handy. If you don't know how to use 30, 60, 90 right triangles, you could use the Pythagorean Theorem. Right? So you'd set up like x squared plus the length squared, right? We don't know what the length is equal to 2x squared. And you get 4x squared. This would be x squared plus l squared. Then you subtract x squared from both sides to get the l squared alone. You get l squared is equal to 4x squared minus x squared is 3x squared. Then when you do the square root of both sides, you'd get that L, right, the square root of L squared is L, is equal to the square root of 3, right, that's the square root of this part, times the square root of x squared is x. So square root of 3 times x, or x root 3. Right, so you could find that even without knowing the 30, 60, 90 right triangle, just using the Pythagorean Theorem. But again, you're given that, and I think it is something worth being comfortable with so that you can get this problem, and problems like it much faster. All right, the perimeter of an equilateral triangle is 852 centimeters. So equilateral, again, means all of the sides are the same, all of the angles are 60. All right, and if all of the sides are the same and they add up to 852, then we could write that as, like, if the sides are x, it'd be 3 times x equals 852. And divide both sides by 3. Get that x is equal to 852 divided by 3, 284. All right, so x, each of the sides is 284. And they say the 3 vertices of the triangle lie on a circle. So it's inscribed in a circle, something like that. And the radius of the circle is w times the square root of 3 centimeters. What is the value of w? All right, so the radius is going to be the center point, or the thing connecting the vertex to the center point of the triangle, which is also the center of the circle. I know I didn't draw this as a perfect equilateral, but we can see that it divides this equilateral into 3 obtuse triangles. You see this one, this one, this one. And they're all going to be equivalent to each other. So they're 3 congruent obtuse triangles. And now we can divide 360 degrees, so this entire center here, by 3, because we're putting it into 3 equal segments. So that's going to make it 120 over here, 120 over here, 120 over here. And then the other angles will be 30, right? They're cutting the 60 in half. So we've got 30, 30, 30, and then 120s in the middle. All right, now we know that this side down at the bottom, which is one of the sides of the equilateral triangle, is 284. And we have this isosceles triangle here, which is 30 degrees, and 120 degrees up top. We want to find the length of the other side, so like basically this part of the triangle. And what we can do is divide this 30, 30, 120 triangle into 2 30, 60, 90s by just dropping this altitude, which is also an angle bisector. And that would cut this 284 in half, so half of 284 would be 142. So we got 142 over here, and then there will be another 142 over here. Now in this case, this is the side of the 30, 60, 90 that's opposite the 60 degrees. So if you had to find the height of this, right, this part right here, that would be 142 divided by the square root of 3. Right, because the ratios of the sides of a 30, 60, 90 are x root 3, and 2x, where the smallest side is opposite the 30 degrees, largest side opposite the hypotenuse, the middle side, the x root 3, is opposite the 60 degrees. Now, again, the x root 3, in this case, is equal to 142. Right, that's the side that's across from the 60 degree angle. We ultimately want to find 2x. Right, so this is our goal, is to find 2x. So first we can divide by the square root of 3 to get x alone, which gives us that x is equal to, right, 142 over the square root of 3. If you want to put that in simplest radical form, you'd multiply by root 3 over root 3. Right, root 3 divided by itself is just 1. Anything divided by itself is 1. But if you multiply by root 3 over root 3, we'll get the radical out of the denominator. So root 3 times root 3 is root 3 squared, which is just 3. And we have 142 root 3 divided by 3, and that should not be divisible by 3. So that's x. We want to find 2x. So that means 2x will be equal to 2 times 142 root 3, all divided by 3. So that gives us 284 times the square root of 3 over 3. All right, so that would be the answer. This is not a multiple choice option. Oh, that is w root 3. Right, they gave us the radius is w times the square root of 3. Interesting. So w root 3 is equal to this long side, this 2x. So if we know that w times the square root of 3 equals 284 root 3 over 3, then what we can do to get w is just divide both sides by the square root of 3. And that will get rid of the root 3 over here and the root 3 in the numerator over here. So we're just left with w is equal to 284 divided by 3. And you could leave it as that, or if you want to give your answer as a fraction, it's going to be a continuing fraction, so you have to round it. But 284 divided by 3 is equal to 94.67. Right? It goes 66666 repeating. Right? Either of those answers should be acceptable. So generally, if you have something that's 0.66666 repeating, you'd round up, but they actually will also accept if you round down. I think it's just to indicate that you didn't like round it, you just basically cut it off right where it was. So that answer is also considered acceptable. I would probably just put it as the fraction answer, but whichever you're more comfortable with, all of them are accepted. An isosceles right triangle has a perimeter of 94 plus 94 root 2 inches. What is the length in inches of one leg of this triangle? Okay. Well, actually, we just did one right before this, so you can even look back to that. Now, on the SAT, you might not have two of them in a row. But we could see the 58, in this case, corresponded to the hypotenuse, and then the 58 root 2 is two of these legs down here. So this one is similarly going to be the same thing. It'll be 94, and then half of 94 is 47. So we'd do 47 root 2 down here, and 47 root 2 down here. So 47 root 2 would be that leg. So you could figure this out by doing... Right, if we know it's an isosceles right triangle, 45, 45, 90, the ratio of the sides is x root 2, like that. So you have to, either the 94 root 2 would be this x root 2, or it would be the sum of the two x's. Now, the reason that it can't be the hypotenuse, right, why x root 2 can't be 94 root 2, was that would mean x is 94, and then to get the perimeter, you'd have to add two x's, and it would be 94 plus 94, so that would be 188, right? So it should be 188 plus 94 root 2. Since it's not that, we know it's the x root 2 cannot be 94 root 2, right? That makes it too big. So the 94 has to refer to the x root 2 side, and then you could use that to find the other side, which would be 94 divided by the square root of 2, right? And that gives you that x is equal to 94 over root 2, and to get that in simplest radical form, you multiply it by root 2 over root 2, which will give us 94 root 2 over root 2 squared is 2. And then half of 94, well, actually, as long as you know it's 94 root 2 over 2, if you have two of those, that would add up to 94 root 2. But half of that would be 47 root 2. So we'd get 47 root 2 down here, 47 root 2 down here, and 94 as the hypotenuse. And then when you add them up, you'd get 47 root 2 plus 47 root 2 makes 94 root 2. And then you'd have the 94 accounted for by the hypotenuse. Right, so that's how you do it. There's two possible options, and again, if the legs were the 94 sides and this was 94 root 2, then you would have more than 94 being added to it. It'd be 188. RS equals 440, ST equals 384, and TR equals 584. Okay, so we've got a triangle. The side lengths of the right triangle RST are given. Oh, it's a right triangle. Now, what we know is the longest side is always the hypotenuse for a right triangle, so the 584 has to be the hypotenuse. And they said that is TR. So we actually already know that S is the right angle. Do they even tell us that? They don't specifically tell us that, but again, if the longest side is TR, then the side across from that, which is S, or the vertex across from that, S, has to be the right angle. RS, they said, is 440, and ST is 384. Triangle RST is similar to triangle UVW. So those would be in the same spots. So R was first, that means U should be first. V corresponds to S, so V is our right angle, and then T is up here. S corresponds to V. All right, we already figured that out based on the order of the letters. T corresponds to W. Oh wait, did I write? I wrote T instead of W, so that actually helped me there. You should be able to figure that out based on the order they write the letters, but I think the SAT likes to specify. So they ask, what's the value of tangent of W? So that's going to be the same as tangent of T, because they're the same angle here, right? If this is theta, then this is theta. So tangent is going to be the ratio of the opposite over the adjacent. The opposite of T and of W would be 440. Now, this could be scaled up or scaled down, but right, if you scale up one side, you're going to scale up the other side the same, so the ratio will remain the same. So we do opposite, 440, over adjacent, which is 384. And it looks like they simplified that. They both will have a 4 in them, so we could do 440 divided by 4 is 110, and 384 divided by 4 is 96. They both are still even, so we could divide 110 divided by 2 is 55, and 96 divided by 2 would be 48, and 55 over 48 is option D. I think some calculators you could just type in the fraction, and then as long as it's in fraction mode, it will return it as a simplified fraction. If you wanted, you could even type in 440 over 384, it will give you a decimal, and then see which of these decimals matches. The main thing here is just being able to figure out that S is the right angle, and like drawing out the triangle like that, and then knowing that if they're similar, T would be the same angle as W, and they'd have the same tangent value. A right triangle has legs with length 24 centimeters and 21 centimeters. All right, so we got 24 and 21. That's not one of the special right triangles, because there is one that's 7, 24, 25, but this is 21, not 7. And there's another one that's 20, 21, 29, but you can't mix and match them, unfortunately. If the length of this triangle's hypotenuse in centimeters can be written in the form 3 times the square root of D, so we'll say this is 3 root D up here, where D is an integer, what is the value of D? All right, so this one I'm just gonna do the Pythagorean Theorem. Again, it's not, to my knowledge, a special right triangle here or a Pythagorean triple. So we'll do 21 squared plus 24 squared equals, I guess we could write it in this form, 3 root D squared. I mean, you could also just solve it first and then figure out what that actually is. I'll do it both ways, I guess. But 21 squared is 441, plus 24 squared is 576. And then over here, 3 squared is 9, and the square root of D squared gets rid of the square root, so it'd just be 9D. So 441 plus 576, I'm gonna use my calculator. I know I could do that, but it gives us 1017. So 1017 equals 9D, and then to get D, we just divide both sides by 9. And 1017 divided by 9 is 113. So D equals 113. All right, I think that's what they're asking for, D. So that's one way you can do it. I didn't even figure out what the actual hypotenuse was. I mean, now you could use that and just go, okay, it's 3 times the square root of 113. But yeah, just putting that in actually kind of made this an easier problem. Now, if you felt more comfortable just going 21 squared plus 24 squared equals C squared, and then using that C to find D, that would work as well. Right? You would still get, on this side, you'd still get 1017, right? 441 plus 576. C is equal to the square root of 1017, because you do the square root of both sides. And then you just have to simplify the square root of 1017. So you can't just type in and get a decimal, because it's not, actually, they probably would accept a decimal answer. So you could just, oh wait, no, they don't, because you need to figure out what D is, right? Oh, so I like this problem then. They'd make you actually figure out the radical, but you'd have to figure out what perfect squares are inside of 1017. Now, they give you this hint that there's 3, so we know that there's probably a 9 in here. There's also a rule with basically, if you want to figure out if any number is divisible by 9, you can add up the digits, and if the digits add up to a multiple of 9, then there's a 9 in there. So 1 plus 1 plus 7 is 9. 9 is a multiple of itself. So we can divide 1017 by 9, and it gives us 113. So that means C is equal to the square root of 9 times the square root of 113. And then, right, we can simplify the square root of 9 as 3. So we have 3 times the square root of 113. And again, they were asking us if C, right, our hypotenuse, is equal to 3 times the square root of D, what's D? Well, we could just see what's in there, what's in the place of the d is the 113. Right, so you get that the same way. You could use this 3 as a hint to help you simplify the 1017. I think it's probably easier just to go straight in, like instead of putting in a c or a different variable like an x or something, just put the 3 root d in there and just make sure you square the whole thing. Right? Don't just square the square root of d, square the 3 and the square root of d, so you end up with 90. And then you can solve it very easily. But either of those are pretty quick. Just make sure that you know your rules with the Pythagorean theorem and with finding radicals. We have rs equals 20, st equals 48, TR equals 52. So this is very similar to the previous one. These are the side lengths of a right triangle RST. So we can see again, the biggest one is TR, this would be 52. And then the next biggest one is ST. So I'll draw it. That one's a little bit longer. Like that. I didn't really draw it that well because this should be more than double the other one, but whatever. And S again is our right angle. We only know that because it's across from the biggest side. Right, so basically whichever vertex is not included in the name of the biggest side, so not included in TR, that's got to be the one that's across from it, so that's the biggest one, or the right angle. The side lengths of right triangle RST are given. Triangle RST is similar to UVW. So again, U will go with R, V will go where S is, and W will go where T is. I almost made the same mistake. Where S corresponds to V, T corresponds to W. What is the value of tangent of W? This is very similar to the last question. They also asked for the tangent of this same angle. Well, it's this same part of the triangle. I know the angle of measure would be different, but tangent again is going to be equal to opposite over adjacent, and T is the same angle as W, so the ratio that it gives is the same. So essentially, they're just asking what's the tangent of T, right? Because the tangent of W is equal to the tangent of T. And we're going to use T because we know the sides that are opposite and adjacent to it. The one that's opposite T is 20. The one that's adjacent to T is 48. So that means that the tangent of W and the tangent of T are both 20 over 48. That's our side ratio. And we just have to simplify that. Those both have a 2 in them. So 20 divided by 2, or actually they both have a 4 in them. 20 divided by 4 is 5. 48 divided by 4 is 12. So, oh, interesting. I didn't even realize this. I know I said I'm usually good about realizing this. This is a 5, 12, 13 triangle that's been scaled up by a factor of 4. Right, so 5 over 12 is the answer. Now, in that case, the 5, 12, 13 part wouldn't really help you that much because you're just doing the side ratios. If you recognize that, maybe it would have made you solve it, a couple seconds faster, but the main thing there is just like the last one that was like this, knowing which one is the right angle, being able to draw the diagrams, and then knowing that if you have two similar triangles, they'll have the same angle measures, and the tangent of the same angle will give you the same value, right? The same ratio of sides. In triangle RST above, point W, not shown, lies on RT. All right, so there's going to be some point somewhere on RT, could be like here. What is the value of cosine of RSW? So we draw W right there like that. So this angle here, minus sine of WST. So what's interesting with this problem, and actually what makes it solvable, is that RSW, so this first angle I labeled theta, and maybe we'll make the other one phi, and WST are complementary. We know that because they're adding up to this right angle, right? They're each part of this right angle. And depending on where you put W, like the angles will change, but no matter what, they still will add up to 90. And now there's this rule where the cosine of an angle is equal to the sine of that angle's complement. So it's equal to the sine of 90 minus theta. And, vice versa, you could do the sine of an angle is equal to the cosine of 90 minus theta. I mean, it's kind of implied because angles are complements of each other. The complement of theta would be the complement of that angle. So essentially what that means is if these two are complements of each other, then the cosine of this angle is equal to the sine of the complement of it. So these two are equal to each other. So whatever cosine of angle RSW is, sine of WST is the same thing. So this is just going to be like x minus x, and it's going to give you 0. All right, and you could check that on your calculator if you don't feel confident in it. You're like, I think this is a rule, but I'm not sure. You could write like sine of 30 is 0.5. And then you'd say, okay, well, what's cosine of the complement of that? Well, the complement of 30 is 60. So cosine of 30, or we said the sine of 30 is 1/2, or 0.5. Cosine of 60, so the complement of 30, is also 1/2. And if you understand the unit circle, you'll see like where this can come from. But you can also just draw a right triangle. If this angle is theta, then the other angle is always going to be equal to 90 minus theta, right? Since this one's already 90, 180 minus 90 gives you 90. So these two have to add up to 90. If this one's theta, this one's 90 minus theta. So say we labeled this A and this B, and this side could be X and this side could be Y, and the hypotenuse could be, let's say the hypotenuse is H. So the sine of A is equal to what's opposite theta is X over the hypotenuse, X over H. The sine of B is equal to, well, what's across from B is Y over H. Now for the cosines, let's do them reversed. So the cosine of B, cosine of this angle up here, which is the complement of A, again, right? A is theta, B is 90 minus theta. Cosine of B would be the adjacent, so that's X, over hypotenuse. So the opposite for A is equal to the adjacent for B, and then they're both being divided by the hypotenuse. Same thing for cosine of A relative to sine of B. The cosine of A, that means the adjacent to A, which is Y, over the hypotenuse. So you can see the sine of A is equal to the cosine of B, and the sine of B is equal to the cosine of A. So it's the same logic here, where we're getting the same thing minus itself. Again, our answer will be 0. So this was just kind of more of a conceptual problem than anything. I'm just more kind of showing ways that you can test that during the test, and then where that would come from. So that proof. In trigonometry, if you haven't taken it yet, you'll learn the unit circle, and that kind of gives you the foundation of where all of these functions even come from, what they mean. Like, why are we doing opposite over hypotenuse? Why are we doing adjacent over hypotenuse? That could also further help you know that the cosine of an angle is equal to the sine of its complement, and vice versa. All right, triangle ABC is similar to triangle DEF, where A corresponds to D, C corresponds to F. All right, did it tell us which one's the... Oh, it doesn't even say the right angle or right triangles. Not even going to draw them as a right triangle. A, B, C. Copy the triangle. Might be a scaled up or scaled down version. We don't know yet. They give more information in a second. This would be D, E, F. So A is the same as D, B is the same as E, and C is the same as F. Angles C and F are right angles. Oh, God, I should have just read a little bit further. It does make sense since the question topic is right triangles. So C is a right triangle, or right angle, and F is a right angle. A corresponds to D, and B corresponds to E. If tangent of A equals the square root of 3, and DF equals 125, so DF is 125, tangent of A is the same as tangent of D. So we could say, right, because they're the same angle, if this is theta, this is theta, so tangent of A equals tangent of D, which equals the square root of 3. What is the length of DE? So we're trying to find the hypotenuse here. To find that hypotenuse, using this tangent part, we could do the fact that that means that tangent of D is equal to EF, which we're not given, over DF. And tangent of D, we just said, is equal to the square root of 3. So the square root of 3 equals EF over 125. That was the given, this DF value right here. So now we can find what EF is by multiplying both sides by 125. And that gives us that EF is equal to 125 times the square root of 3. Now, hopefully, if you've been watching the video through and not skipping just to this problem, hopefully you'll recognize this because enough of these have come up in just this video alone. This is a 30, 60, 90 right triangle because we've got the 90-degree angle and we've got an x to x root 3 ratio of sides. I know I didn't draw it perfectly well. Right, if I drew it more like that, 30, 60, 90, the ratio of sides for that, the side opposite the 30 should be x, the side opposite the 60 should be x root 3, and the hypotenuse should be 2x. So we know this has got to be the 30-degree angle because it's across from the small side, the 125, and this angle I labeled theta, the angle D, it's got to be 60 degrees. Same thing up here, A is going to be 60 and B is 30. That doesn't really matter, but just to show they're still similar triangles. And again, the reason I realize that is we've got x and x root 3, where x is 125 in this case, right? This is the ratio of sides, that this side, this leg, is square root of 3 longer. Now that's also true, you could start to recognize if you've done enough of these trig functions, that if the tangent is equal to the square root of 3, for a right triangle, then that means that the angle is a 30, or that the triangle is a 30, 60, 90. Now you could do the other angle, in which case it would be 1 over root 3, which simplifies to root 3 over 3. But either of those, if you get tangent equals root 3 over 3 or tangent equals the square root of 3, that tells you it's a 30, 60, 90. But you'd also recognize that from the unit circle, because a lot of the triangles on a unit circle are 30, 60, 90s. So if you can recognize this part, then you don't even need to do the Pythagorean theorem. Because the other way that you would find DE is just do 125 squared plus 125 root 3 squared equals DE squared. Solve for DE that way. But if you recognize that it's a 30, 60, 90, you just double this small side. So double 125 gives you 250, right, which would be this answer right here. All right, I'm just going to show, I guess it doesn't take that long. I'll just show that you could do it by just squaring these. 125 squared is 15,625 plus 125 squared here would be 15,625 times the square root of 3 squared is just 3. So we end up getting basically 15,625 times 4, because you got 1 here and 3 there. Or you just add those up. That gives you 62500 is equal to DE squared. Which, if you realize this is actually 25 squared. So you get 25 squared and then times 100, which is 10 squared. So it's going to be 25 times 10 when you do the square root. But I'll type that in the calculator just to show it as well. So if you do the square root of 62,500, gives you 250. So DE is equal to 250. Right, so that doesn't take that much longer than doing the 30, 60, 90. I know, I was talking about the 30, 60, 90 for longer than this even took. That's just because I'm trying to explain the logic of it. But if you recognize it, then you just go really quickly. Oh, 30, 60, 90. So this hypotenuse is going to be double the short side. So it's double 125 is 250. Right, so you could do it like basically instantaneously. All right, so let's say you do that one. You can see that there's a pattern here that a lot of these are 30, 60, 90 special right triangles. So make sure you're comfortable with those before you go into the SAT. The length of a rectangle's diagonal is 3 times the square root of 17. We draw our little rectangle here. The length of the rectangle's shorter side is 3. So we got 3 there. So our diagonal is 3 root 17. What is the length of the rectangle's longer side? So we're just trying to find this here. And you would just use the Pythagorean theorem. We would say 3 squared plus x squared is equal to 3 root 17 squared. So 3 squared is 9. X squared we just leave. 3 squared is 9, and the square root of 17 squared gets rid of the square root. It's just 9 times 17. So we'd subtract 9 from both sides. You get x squared equals... Now, I'll show you a little trick here. You could just type in 9 times 17 minus 9. But we actually have, in this case, you could say there are basically 17 nines, right? 17 times 9 is just like you're adding up 9 17 times. And if we take one of those 9s away, then you're left with 16 nines. So 9 times 16, right? I mean, again, you could also just multiply them out and get the actual number. But now when we do the square root of x squared, we can do the square root of this without multiplying it out. And the reason I'm leaving that is because 9 and 16 are both perfect squares. So the square root of x squared is going to be x. The square root of 9, and the square root of 16, the square root of 9 is going to be 3. The square root of 16 is going to be 4. So we get x equals 3 times 4. So that means x is going to be 12. Right? And you can verify that 3 squared plus 12 squared should give you the 3 times the square root of 17 squared. Now again, if you want to just do it the normal way, not be weird about it, 9 times 17 gives you 153. And then when you subtract 9 from that, it's 144. So you'd say x squared equals 144. I think most people would recognize that's the square root of 12. If not, you could just type it in your calculator. So x will be the square root of 144, 12, right? You hit it the same way. That might actually even be faster. I just thought this was kind of neat. I think this is like an error. I don't know what's supposed to be there. That doesn't necessarily mean it's one of the wrong answers. It could just be like, these are all the problems from the SAT online question bank. And I guess they have some that still have errors on them. But which of the following expressions is equivalent to sine of 24 times cosine of 66 plus cosine of 24 times sine of 66. All right, well, this is that same thing that we were talking about, I think, before, because these are these complements of each other. Although now we're multiplying them, which is a little bit interesting. I do think this might be impossible to answer, because I don't think it's one of these two. I think it's going to be one of either C or D, but we don't see what that is. So I'll just solve it, or I'll find something that's equivalent to it. But we know that the sine of 24 is equal to the cosine of the complement of 24, which is 66, right? Because 90 minus 24 equals 66. Same thing over here, right? The cosine of 24 is equal to the sine of 66. So we could essentially write this as sine of 24 degrees squared plus the cosine of 24 degrees squared. Or likewise, you could write it as the cosine of 66 degrees squared plus the sine of 66 degrees squared. Right? Those will be the same thing, right? Because the sine of 66 equals the cosine of 24. Now, it looks like they're doing here that the answer's got a 24 at the end. I'm guessing it's saying that this is going to be c, and the thing that goes in this m sup is sine of 24 squared. But, you can't actually tell because there's also a sine of 24 squared here. But I'm just like to keep the order, right? Because the cosine of 24 squared corresponds to the second one, so I doubt they'd flip them. So I'm guessing it's supposed to be c. Let's just rule out if it is one of these ones. So there's also another thing. I don't think this will matter, but if you have the sine of something squared plus the cosine of the same angle squared, like that, if you draw a right triangle, right, and say this is 24 degrees. Now, if we take the sine of 24 degrees, right, opposite of our hypotenuse, say the hypotenuse, we treat the hypotenuse as 1, right? So it's like a unit circle. So this is the sine of 24 degrees then, because it's the opposite over 1, right? So it's sine of 24. Then this would be the cosine of 24 degrees. So if you do the sine of 24 squared plus the cosine of 24 squared, that should be equal to the hypotenuse squared, which, right, for the unit circle, which is where these come from, would be 1 squared. So the sine of an angle squared plus the cosine of the same angle squared equals 1. So they really could have an option here that just says 1. I know they don't. But I'm trying to think if one of these things is equivalent to 1. Well, for this one, this angle times itself times 2. No, that doesn't make sense. Let me just check what they're looking for. Again, this one, like, you really can't answer it because you're seeing the options. Like, if it just said to solve it, then you could just solve it without looking at the options. But because they're asking which one is correct, C is correct. Is that what we said? Cosine of 20. Yeah, I think that's because we said the cosine of 24 squared should be second. So I assume that means it's supposed to be sine of 24 squared. But they could have also made it 1, right? There's no... This is kind of implying that the two are equal to each other, because you're just doing this one plus this one, so 2 of them, but they're not, like, sine of 24 is not equal to cosine of 24. It's equal to cosine of the complement of 24, so cosine of 66. So that one's not true. And then this one is saying, like, instead of, this would work if these were squared instead of times 2. But when you multiply something by itself, you square it, you don't multiply it by 2. So it's not B. And then again, we don't know from this what D is supposed to be. I assume that this is going to be, maybe this is supposed to be sine of 66 squared, which is, that would be true. So maybe it's cosine of 66 squared. I don't know what they wrote here. Whatever. This one, again, is a lousy problem as it's written, but it should say either sine of 24 squared plus cosine of 24 squared, or they could just say 1. I don't know if they test that concept on the SAT, though. I haven't seen that show up before, where, like, sine of an angle squared plus cosine of the same angle squared equals 1. It could show up, though, in your trigonometry or pre-calc class, and it might be something that will be important in calculus if you haven't done that yet. A square is inscribed in a circle. Let's draw a circle first, and then we've got a square inscribed inside of it. Make that a little smaller. Okay, I don't inscribe that perfectly, but imagine it is inscribed perfectly. The radius of the circle is 20 times the square root of 2 over 2. Right, so that's half of the diagonal of the square. The diagonal is the diameter. What is the side length in inches of the square? Okay, well, what I just said, the radius equals 20 root 2 over 2. That means that the diameter is double that. Right, so double 20 root 2 over 2, you just don't divide it by 2, so it's just 20 root 2. It's interesting, they could have just written this as 10 root 2. But whatever, you double it, it's 20 root 2. That is the diagonal of the square. And a square is made up of 2 45, 45, 90 right triangles, like stacked on top of each other. So this would be 20 root 2. And then, right, if you know the ratio of the sides, it's x root 2. for an isosceles right triangle. So the x root 2 is 20 root 2. That means that x is 20. So what is the side length? It's just 20. I think there's another one that's given to you, like the ratio of these sides. If it wasn't, then you could just say x squared plus x squared equals 20 root 2 squared. Right? Use your Pythagorean theorem. And then you could solve for x. You get the same thing, that x equals 20. Right? You get 2x squared equals 20 squared is 400 times square root of 2 squared is 2. And then just divide both sides by 2. You get x squared equals 400. And then the square root of 400 is 20. So x equals 20. Right? So either way, whether you use your special right triangle, the 45, 45, 90, or if you use the Pythagorean theorem, you'll end up with the side length of the square is 20. Triangle ABC is similar to triangle DEF, where A corresponds to D, and angles C and F are right angles. Okay, let's draw two similar triangles. So I will copy this one and paste it over here, and maybe make it bigger. I don't know if it's bigger or smaller yet, but we've got C and F are the right angles. And they said A corresponds to D, right? Those are both written first. And then B must correspond to E. Yeah. Now, the length of AB is 2.9 times the length of DE. Oh, so I did this backwards. This one should be smaller. Let's do it like that. We call this x, and this will be 2.9x. If tangent of A equals 21 over 20, so tangent is opposite over adjacent, then what is the value of sine of D? Okay, well, they're trying to throw you off with I don't think the scale factor thing will matter at all, because sine, tangent, right? The trig functions just deal with the ratios of the sides. It doesn't actually matter what the side lengths are. So they're trying to throw you off with that. Don't let them do that. But the ratio of the sides, so tangent of A, opposite over adjacent is 21 to 20. Now we don't know if it's actually 21 to 20, but that's like, what the ratios are. Which would actually mean that this is 29. So this is another Pythagorean triple. 20, 21, 29. And if you don't know that, just, right, you could figure it out this way. Right, so I'll write AB squared. 20 squared is 400. 21 squared is 441. So that's equal to AB squared. 400 plus 441 makes 841. And then to get AB, you do the square root of both sides. And the square root of 841 is going to be 29. Now, if you didn't know that, you just type it into a calculator. You figure it out. 20, 21, 29. Again, we don't know if that's actually the side lengths, but it doesn't matter, right? It could be 200, 210, 290. It could be, right, like fractions or something, but we're just looking at the ratios of the sides. There's nothing about the areas or actually finding a side length. And that, again, we could go, oh, well, this one's 2.9 times the length, so that this should be 10 and this should be, it doesn't matter, right? It's just about the ratios of the sides. So this is 20, this is 21, this is 29. If you want, just treat these as if they're all 2.9 times bigger. Right? I think they're trying to throw you off with that 2.9 so that you treat this DE as a 10, which you don't want to. So tangent of A is 21 over 20. So the same thing, tangent of D would be 21 over 20 because they're the same angle. And now we want to find sine of D. Well, the sine of D is equal to the sine of A. So you do the opposite over the hypotenuse. Right? Sine of an angle equals opposite over hypotenuse. In this case, your opposite is the side that's 21, and the hypotenuse is 29. Again, it doesn't matter if that's actually 21 or 29. The ratio of these two to each other is 21 to 29. So it's 21 over 29 will be your sine of D. You just write it like that. If you want, you could type that in your calculator and change it to a decimal, but there's not really any point because they accept it as a fraction, and that's already fully simplified. In a right triangle, oh, and I guess I'll just specify this one. So again, it does help to know your Pythagorean triples that could come up. So we've seen a couple of them now. So 5, 12, 13 has come up a few times. 3, 4, 5 came up. Both of those came up scaled up most of the time. 20, 21, 29 came up. And I believe there's another one. There was 12, 35, 37. So 12, 35, 37, and 20, 21, 29 are two of the more obscure ones. A lot of people won't know those unless you maybe did math counts, something like that. But even if you don't know them, you can always figure out the third side once you have two of them, just using the Pythagorean theorem. It just could potentially save you a little bit of time. In a right triangle, the tangent of one of the two acute angles is the square root of 3 over 3. So I know, we actually just talked about this in a previous problem, maybe a few questions ago, that if your tangent is either the square root of 3 or the square root of 3 over 3, that means it's a 30, 60, 90 right triangle. Now I'll act like I don't already know that, but you might want to train yourself to see that. If it's a tangent is this, then that would mean it's a 30, 60, 90. What is the tangent of the other acute angle? Well, it's actually going to be the tangent of the other acute angle. It should be square root of 3, I would think. 3 over the square root of 3 is, oh, this is a weird way of writing it. This is the square root of 3 right there. All right, so it's going to be D, I assume, but let's just verify that first. So if you draw a triangle, this is like angle A, and this will be angle B. So tangent of A, that's going to be opposite, right? Tangent is opposite over adjacent. It would be square root of 3 over 3, right? Opposite over adjacent. If you do tangent of the other angle, that would be the opposite. In this case is the 3 over the adjacent, which in this case is the square root of 3. So it'd be 3 over root 3. So, actually they're being nice by doing that, leaving it in an irrational denominator, because, right, if you don't even need to know it's a 30, 60, 90. What might throw you off is the square root of 3 times the square root of 3 is 3. So this would actually be the 60-degree angle. This would be the 30-degree angle. So the tangent of 30 degrees is equal to root 3 over 3. The tangent of 60 is what you could write as 3 over root 3, but that's equal to the square root of 3. All right, so interesting enough, you don't need to know it's a 30, 60, 90. So I was trying to make it as if I didn't know that, but actually not knowing that technically makes it easier, or right, not using that makes it easier, I would say, a little bit. All right, 3 over root 3. And then here we have triangle ABC is similar to triangle DEF, where A and D correspond and C and F correspond. Does it say which one's the right angles? Oh, angles C and F are right angles. So C is a right angle, F is a right angle, and then we have A corresponds to D, and B would have to correspond to E. If tangent of A equals 50 over 7, so I'm going to write it as tangent is opposite over adjacent. I'm going to just write these numbers on here. Again, they're just ratios of the sides, so the sides don't have to be this, but it seems like most of these questions don't have to deal with the side lengths or the areas. So 50 to 7, right? That's the ratio of the sides, which also means the ratio of these sides would be 50 to 7, right? Because they're similar, so the ratios of the sides are the same. I should probably write 50x, 7x, and I could write like 50y, 7y over here. It doesn't really matter though. What is the value of tangent of E? Tangent of E, well, E is right here. So tangent is opposite. In this case, opposite of E is 7 over adjacent, which in this case is 50. So it's just 7 over 50. So all you have to do there is just kind of keep track of, which sides match up to which, and then just understand how to do tangent. And it doesn't matter that this side is probably not exactly 7 and this one's not exactly 50. That's the ratio of them. Right? So if I'd written it as like 7y and 50y, like I said, and this is 7x, 50x, then when you do opposite, it would be 7y over adjacent is 50y, and the y's would just cancel out. You'd still be left with 7 or 50. So that's why I'm saying it doesn't matter. If they were asking for the length of the sides, then it would matter. Or if they're asking for the area of the triangle, or something that depends on the actual exact length of the sides. In the figure above, BD is parallel to AE. What is the length of CE? All right, well, we could see these are going to be, if they're parallel, then these are going to be similar triangles, because that means this is 90, this is 90, right? If two parallel lines are cut by the same line and one of them makes a right angle, the other one's a right angle, and right, these would be corresponding angles of a transversal through two parallel lines. C is the same as itself, right? So we've got two similar triangles, and the scale factor to go from this little triangle to the big one is 3, right? We have to multiply 6 by 3 to get 18. Right? You could do 18 divided by 6 if you didn't see that. Now, we know this side is 8 on the little triangle, so if we multiply it, that would make this whole thing AC equal to 8 times 3, which is 24. Right, so this would be 24. What is the length of CE? Okay, well, CE is just going to be the hypotenuse of this right triangle. We already have the side 18. We just found that this one's 24. Oh, or you could say it's a 3, 4, 5. Yeah, that's the better way to do it. So it's a 3, 4, 5 scaled up. Right, so this one would be 10, because because it's 3 times 2, 4 times 2, 5 times 2. For the big one, it's scaled up by a factor of 6, right? So we have 3, 4, 5, and we scale it up to be 3 times 6, 4 times 6, so 24, 18, and then 5 times 6, which would be 30. So that's all you've got to do there. Recognize that it's a 3, 4, 5 scaled up, and your side would be 30. Now, if you didn't realize that, you could just do 18 squared plus 24 squared equals CE squared, do the Pythagorean theorem, and you would get that 576, that's 24 squared, plus 18 squared is 324. That would add up to 900. So that's equal to CE squared, and then the square root of 900 is 30. Right, so you get the same answer either way, but recognizing the 3, 4, 5 is probably the easier way. In triangle JKL, cosine of k equals 24 over 51. Angle J is the right angle. So if you do too many of these in a row, you're just going to think every triangle is a right triangle, because that's what all of them are. But we've got JKL. Cosine of k is 24 over 51. Cosine of an angle is equal to the adjacent over the hypotenuse. So adjacent to k would be the one that's touching it, that's not the hypotenuse. That should be 51. And the hypotenuse is just opposite the right angle. What is the value of cosine of L? Okay, well, this is not a Pythagorean triple. There's no one that is 24 and 50. Oh, actually, they're both multiples of 3. So 51 divided by 3 is 17. We can say this is 17 times 3. 24 is 8 times 3. So this is a Pythagorean triple. 8, 15, 17 is one of them. 8, 15, 17. You could do 8 squared is 64 plus 15 squared is 225. 25 plus 64 makes 289, which is 17 squared. So that would mean that this has to be 15 times 3. Are they just asking what's the... Oh, they want the value. So with that, that would mean that this side is going to be 45. You could also do like 24 squared plus JL squared equals 51 squared, and you'll end up with the same thing, that JL equals 45. It'll be JL squared equals 45 squared, whatever. But once we have that this is 45, or you could even know it's 8, 15, 17. So L corresponds to this angle over here. That's the ratio of the sides, 8, 15, 17. They're all scaled up by 3, so the 3's would cancel out. But let's call this phi. So the cosine is the adjacent, so this side over this side. And we could write that as 45 over 51, and then simplify it, right, to 15 over 17, or just, again, the ratio of the sides would be 15 over 17. So that's your answer. All right, so that's another another Pythagorean triple that showed up. That this one is one that I'm more used to showing up, but I haven't seen it scaled up like that in a problem. Remembering Pythagorean triples really could help, or at least having practice using them. Again, if you didn't use them, you could just use the Pythagorean theorem and it would still work out. Just make sure when you get 45 over 51 that you remember to simplify that, because those are both multiples of 3. You could also just type it in to your calculator and do it as a decimal. But in the triangle shown, what's the value of cosine of x? Well, cosine is just adjacent over hypotenuse. So cosine of theta equals adjacent over hypotenuse. There's a second one like this that I really feel like could have been even in the easy section potentially. Here's some of the other ones. So adjacent to x is 11, and the hypotenuse is 28. So it'd be 11 over 28. That's your answer. That's already simplified. A triangle with an angle measure of 30, 60, 90 has a perimeter. Okay, so this is a special right triangle. 30, 60, 90 has a perimeter of 18 plus 6 root 3. What is the length of the longest side of the triangle? Okay, well, the 6 root 3 is this side, because the ratio of the sides is x, x root 3, and 2x. And you could say, well, it's possible that the square root of 3 is both of these and that the integer would be this one. That could happen, but then it wouldn't be so much smaller like this. So if this is 6 root 3, the small side is 6, and the other side is 12. 6 plus 12 makes 18, so that checks out, and then plus 6 root 3. And then they say, what's the length of the longest side of the triangle? That's the hypotenuse, so they're looking for the 12. All right, so that one, just know your 30, 60, 90s like the back of your hand, and a lot of these will be really easy. And that's our last problem. All right, so again, those special right triangles, 30, 60, 90s came up a lot. There were a fair number of isosceles right triangles, although, for both 30, 60, 90s and isosceles, if you don't know how to do them, or if you don't remember them, they should give you a reference sheet, and you could also derive them using the Pythagorean theorem. They had the equilateral triangles came up. There are a lot of just basic trig functions, sine, cosine, tangent, and basically knowing how to apply them to similar triangles. And Here's another similar triangle. Nothing was too crazy though. Knowing the ratios, knowing tangent. They had a couple of questions. There's also, or there were two, I think, with a rectangle inside of a circle, and then there's a square inside of a circle. I can't remember if there's a right triangle inside of a circle, maybe. I don't remember. Basically recognizing that the diameter of the circle is going to be the diagonal, or say it was a right triangle, that would be the hypotenuse. So that's something that you could use, and if you figure out what the diameter is, you can find the diagonal and then use the diagonal to find the sides. Or if they give you the side or the diagonal, you could use that to find the diameter and then the radius. All right, here's another one. I mean, this one wasn't even in a circle, but you just use the Pythagorean theorem there. And, oh, this rule. So this only came up in this one problem, or I guess it also was in that one that had the M sup, the thing that was, yeah, this one. So just that rule that the sine of an angle times the cosine, or not times, the sine of the angle is equal to the cosine of the complement of that angle and vice versa. So make sure you know that rule. And let's see, number 12. Knowing Pythagorean triples can come in handy. It's not necessary, but it can come in handy. They had a fair number of them on here. There was 8, 15, 17, 3, 4, 5, of course, 5, 12, 13, of course. And then 20, 21, 29 came up, 12, 35, 37 came up. I've had previous videos that go through all of the most common ones. The other ones that didn't come up on here were 7, 24, 25, 9, 40, 41. But we also had 8, 15, 17 came up on this one. But let's see. Besides that, oh, this problem was a little bit tricky. You ultimately used 30, 60, 90, but this was one that, yeah, had a triangle inscribed inside of a circle, and it was an equilateral triangle. So equilateral triangles came up a fair amount. I think there were two that had to do with areas of equilateral triangles. So make sure that you would know how to find the height of one, because once you have the height, then you can find the area, and you just use 30, 60, 90s to find that. And besides that, that's another height of an equilateral. There's the equilateral area. Oh, knowing this trick that if you don't know how to do radicals, now I know being comfortable with radicals will help a lot on the geometry section, but if you don't know how to do radicals, or if you get your answer as a fraction, they want it as a decimal, something like that, or you get the answer as a decimal and the choices are not decimals, just plug in all the answer choices and see which decimal answer matches. So that's just a useful trick in general for SAT math. And yeah, that's the gist of it. So these were all of the right triangle and trigonometry geometry problems with hard difficulty. There'll be one more geometry video coming that has all the circle questions as well. But if you have any questions or concerns, if you have an idea for a better way to do one of the problems, or if you have a specific problem that you would like me to revisit or something like that, feel free to comment below. And thank you for watching.